Hello, everybody. We're going to talk about 7.8 exponential models. So we're going to use differential equations to model some exponential functions. So you might remember exponential growth or decay. I think in one of your earliest classes, you've seen this like P e to the RT, that kind of idea. So we're going to use our differential equations to prove kind of where this formula comes from. That's kind of the idea of what we're going to get to today. And we need to be able to recognize a few different situations. So the first big one is in this box, it says the rate of change of a quantity. So the change in a quantity is proportional to the size of the quantity. All right. So when you see this proportionality statement, then we know we're dealing with exponential growth or exponential decay for that matter. So take a look at number one. I want you to see kind of how it's worded in a sort of application setting. So it says, for number one, it says the weight of an animal is increasing at a rate proportional to its weight. So the weight is increasing. So I'm going to say dW, so the change in weight over time is going to be proportional. So I'm going to have this K value, this constant of proportionality, times weight, right? And notice it's always the Y value. So the rate of change is proportional to the output, to the Y value. So that would be my differential equation. All right. So for number two, same idea. So it says a bacteria population is shrinking at a rate proportional to its population size. Now, if I do this, the bacteria population, so I'm going to say, let's say dB for bacteria over dt is going to equal K times the population size, which would be just the number of bacteria again. Now, for this one, note, K may be negative because it's going to decrease, right? So if it's something that's getting smaller and smaller, your K value may end up being a negative value. If it's increasing, your K value will end up being a positive value. Now, I do want to show you kind of the relationship. So this is kind of your formula, if you will, for exponential models. And I want to show you why it's a formula for exponential models. So if we did this with separation of variables, so I have a dy over dt equals ky, I'm going to separate. I'm going to bring the dt over. So I have a dy equals ky times dt. I'm going to divide the y. So I have a 1 over y dy equals a k dt. Now you're probably wondering, well, why didn't you move the k as well? K is a constant, so I don't want to make the left side of my equation any more difficult than it needs to be. But I am going to integrate both sides. And the antiderivative of 1 over y is just going to be the natural log of y equals the antiderivative of k. Well, k is a constant, so I'm going to get k times t. And then don't forget your plus c at the end. Now, they did not give me a point. In some of the future problems, we will, so we'll find out what that constant is. But if we do this, we're going to get rid of our natural log using base e. So I have the absolute value of y equals e to the kt, and then that plus c is now in my exponent. So here's where we have to talk about some exponent properties. I have the absolute value of y equals e to the kt times e to the c, right? Because if you have two things, two powers of the same base being multiplied, you would add their exponents. So I'm going to have the absolute value of y equals, now e to a constant is just a constant, to the kt. Now I want you to compare this to what you guys did in earlier classes in algebra 2, pre-calc, whatever the case, right? So this is a formula that we knew for exponential growth, and this is what we get when we solve that differential equation. Notice C is just going to be my initial value, K is my rate, and then the Y would be what I get as the end. Okay? All right. So if we take a look at this, so I know with the way that this is set up, okay, look at how this differential equation for number 3 is written, right? dy over dt equals 6y, right? So I know, change markers here. My k has to be 6. All right. So if I start to write my exponential equation, I'm going to have this c e to the 6t, right? So now I'm just going to plug in my information to find c. Now t is 0. So I have y equals ce to the 6 times 0. And that actually, I shouldn't put a y because that's going to have to equal 5. So I get 5 equals c times 1, or in this case, c just is 5. So my function has to be y equals 5e to the 6t. And ladies and gentlemen, that would be the exponential model. Now, you don't have to go through this separation of variables each time, but if you did, you would still get to the same answer, okay? So again, I want you to notice dy over dx is equal to negative 3y. Notice the output is proportional to the output. So I can use that exponential model. So y equals ce to the kt. And I know my k has to be a negative 3. And I should probably say negative 3x, right? So I'm talking about x values. So now I'm going to plug in what I know to get the particular solution. And I get a positive 4. Let me change colors here as well. So I get a positive 4 equals c e to the 0, which is just c times 1. So in this case, c has to be 4. Now, don't always think that it's just that y value. It's just, notice it's our initial amount. So if you relate it, your initial amount is typically your c value. But if I were to say x equals 1, then we would have to kind of do a little solving there. But my final equation is going to be y equals my c value, which is 4, e to the negative 3x. And ladies and gentlemen, that is my exponential model. Okay? So let's put in a little bit more application setting. So an animal weighs 3 pounds at birth, 4 pounds just 3 months later. So let's write down. So in the beginning, so I know at birth, that animal weighs 3 pounds. 3 months later, so we're talking in months, it's going to be 4 pounds. The weight of the animal is increasing at a rate proportional to its weight. So that is your clue. That is your reason for using exponential growth or decay. So I know, let's say I say the change in weight with respect to time, because we're talking in months, is going to equal k times the weight, right? Now, I don't know what k is, but what I do want to do is I want to kind of set up and solve. I want to find out what k is. I want to find out what c is. I want to find out what all this is. So based off of this statement, I can make my equation be, well, the weight is going to be ce to the k times t. And I know 2 points. So I'm going to say, well, 3 is going to equal to c e to the k times 0, or 3 equals c e to the 0 power, which in this case, 3 is going to be just c, right? But I also know that I have the 0.34. So if I do this, I can do it again. So it's 4 pounds. I know what c is. I just need to find k. So t is, 3. Let me write that a little neater here. Start to write a 4. So I get 4 equals 3e to the 3k. I'm going to divide the 3 over. Now, these numbers typically don't come out very nice, just a heads up. I'm going to take the natural log of both sides, and then I'm going to divide by 3. So I get the ln of 4/3 all over 3 is equal to k. So now I can write my equation. I know c is 3, e to the, now this is a terrible number, I'm aware, okay, times t. But I can now plug in a 5 into that, and it will give me the weight that I'm looking for, oops, all over 3 times 5, and that's all in the exponent, and that will equal my weight, okay? So the highlighted section at the top, that tells you you can use exponential growth or exponential decay. That tells you that we can set it up using that exponential model. All right? All right. So if you have a positive exponent, it's growth. We kind of discussed that. If you have a negative exponent, it's decay. So we kind of discussed that. The only thing I want you to kind of watch out for is like doubling or half-life. So if something doubles, that just means I'm going to have twice as much. So they usually, when they give you doubling or half-life, they give you a little less information because doubling is pretty straightforward. So it says the population of y grows according to the equation. So that they gave you the differential. So I know I can use that exponential model. I'm going to say y equals CE to the KT, right? And K is a constant. T is measured in years. If the population doubles every 7 years, what is the value of K? Now I'm going to do a little writing here just to make sure you understand. So C is my initial value, okay? Where y is my final value. All right. Now I know that after 7 years, okay, that this is going to double. So if I started with 1, I'm going to get 2. If I started with 5, I'm going to get 10. So whatever I start with, notice they don't give me an initial amount, but it doesn't really matter because whatever I start with after 7 years is going to double. So I'm just going to say 2 equals e to the 7k. Now, if you were doing half-life, then it would be 1/2 equals e to the 7k, right? If you were tripling, it would be 3 equals e to the 7k. But then we can just solve it, right? So I get the ln of 2 equals 7k divided by 7, and I get my k value to be the ln of 2 over 7. Okay, and that is your exponential lesson. So there are a bunch here, so you can practice finding the particular solutions. These are all exponential, and then a couple word problems for you to give a try to. I will post the answers to some of these practice, and then there's some multiple choice prep if you want to try those out. I think they're pretty good practice for this particular topic. So hopefully that helped, and I'll see you guys soon.